Right, people, it's already nearly 6 minutes past 8. At the first stage, we are only 9. That means there's not a quarter of your guys is in class. I do not want to waste your time. I know. I think maybe the reason is because it's long weekend and people is on his way home. I see now. Okay, it looks like it's to start climbing now. It's now you're now already 11, but we are not. We're far less than 50%. Yesterday, I think it was something in the 30s. And that's what I said earlier this morning to your other guys who was there. This part of the work is very important. I do not want to go through this part of the work. I mean, I must done everything again next week. Wednesday again. That's why I think we must make a decision. I do not want to wasting your time, or we must still waiting for another 5 to 6 minutes and see if there's still people coming. I see already. Okay, we're now already 17. From your side, I want your guys to make a decision to tell me yes, continue, or no. Let me wait till next week, Wednesday. I do not know if you have other classes later today, because I understand some of the lectures have already indicated to students there's no classes because it's long weekend. Everyone is on his way home or on holiday. Who is the class rep of this group?
Garrett Botha, sir.
Garrett Botha. And that guy is not in yet.
Yes, sir. No, I am, sir.
Where you am? Right. Oh, I didn't see you. Are you log in on the other name? Because I can't see a Botha here.
No, sir, I'm in my account.
Is it okay? Right. Well, oh, where are you? Okay, where is you? Okay, you are a class rep. I think from your side, you must make a decision. We have a group. Do we continue, or will we wait till next week on Wednesday and then start with the second part of this work? There is, see, there's now already 20 in online. Do you think I must continue?
Some people are saying in the group next week, but I'm unsure, sir.
Come, people, I want to hear from other people as well.
Personally, to me, we're already logged on, so we might as well just do it. Either way, we need to get through the work.
Okay, all right. I think if people feel we must continue. Is it right? I'm right. We must continue.
Yes, sir.
Okay, right. Okay, people, let me show me your screen. One thing what I said yesterday after some of you guys maybe left already, you see there on my screen now is a blue book. If you are coming sometimes to campus, please come around the office and come and collect your blue book. You will sign for the book. When we are doing the last chapter about sex and moment of areas, then you will need this book. That's why it's important, people, in the meantime, come and collect your book. All right, that is important. It's a blue book like this. It's some tables, what we will use when we are start with the last chapter regarding sex and moment of areas. Okay, all right. What we have done yesterday, we have working with one piece of material, and then we said if there's no stress in the material, but you heat up the material, there will be a change, what we call the free change, and that was your formula. And then also the other one was when you add a load on, then we say, we call that the mechanical one. You'll see at this stage, I use an X because I have a difference between the two, because today we will combine this two with the next part of the work. Then people, you can, if you're working through Wiley Plus book and other books, most of the books are working with the force. Because if he asks you to calculate the stress, most of the guys is working with books, working with first with a force, and then from there he calculates the stress because the stress is force over area. But otherwise, you can directly use this one if I ask you what is the stress. Right, so that is what we will look into today. We will start to combine these two. Also, what we have done yesterday was that we have said we have a temperature, there's no stress standing there. Then it was a free change. Then I will use a force to bring it back. Then it's my mechanical change. And if it's not going back to the original position, then we have a allowance also. This is also what we have done yesterday. And then finally, yesterday, we have the two formulas to calculate the stress and also the one with an allowance. And that is what we have done yesterday. That is the one for my stress with my mechanical and my free change are equal. Get this, my formula they can use to calculate the stress. Or when I have allowance, I can use this formula. All right, this is what we have done yesterday. But people, again, I said, remember, this is when you have one material. Today you will see I will start to combine materials. We have more than one material. We will start to put it in a parallel, or you can put it. It can be in series. But I will show you now how to from a drawing how to define for yourself a formula. All right. What we will do today is, and I will use more than one color. We say we have, let me say we have a steel pipe, for example, with inside here is a copper piece of metal. Right. And then we also say that is my original length from there to there. That's my original length. Okay, this is what we will do today. Now we have more than one material. Okay. The question on the end of the day, the question will say, calculate the stress in the steel, and also I want the stress in the copper. That is my two question. That's a question what I will ask you. Now, people, what happened now is what you guys are doing, and that is the wrong way. You go and you say, okay, I use my steel one. I use this formula, and I calculate it. And then the same with a copper. That is wrong. That is totally wrong. Please do not do it. And it happened every semester. All right. Now, the first thing what we know we have two changes. We have a free change and we have a mechanical change. And we must combine that. And remember, when I calculate these two stresses, that means that two stresses, it must at the same point. It can be at other point. It must be at the same point when I calculate that one. All right. Okay. First thing what I do is I say, okay, I heat it up to a certain temperature, and then what happening is my steel one maybe change till that point there. And I say from here to here is my free change for steel. It's from there to there. That's my free change for steel. All right. Now, people, this is where I said to you, the coefficient of a material will tell you which one is the softer material. Now, always, when we come at a point, and you didn't know which one is, the one with the highest coefficient will be always the softer material. Right. In the case in verse 2, I think you know that after manufacturing, is that between steel and copper, and also at school days or physics, you know the copper one is the softer material as the steel one. That means when I hit it up, heat free change will be more. Maybe stop there. Depend on what is the temperature. Right. That is my first part. When I have a free change. Okay. But when I want to calculate this stresses here, I must do it at one point. All right. Now I say, let I have a line here, y, and I use a load, a load of steel, that is equals to a load of copper. All right. Because I want to bring my steel one to this point, and I want to bring my copper one to this point. But that load, that force must be equal. I can't have a different force. That must be an equal force to bring it here. That means now this one will going that up to that point there, and I call that is my mechanical change for my steel. That's my mechanical change for my steel. And I will bring this one back here, right? And that part here, from here to here, will be my mechanical one for copper. Right. Okay. Now I say, at line YY, will I say my free change for steel plus my mechanical change for steel is equals to my free change for copper minus my mechanical for copper. Right. Because at this line, I want to know what is my stress at this point there, because my two materials must be at the same point. Right. Then we can say my mechanical one for steel plus my mechanical one for copper is equals to my free one for copper minus my free one for steel. Right, and then we know stress L over E for steel plus stress LE for copper is equals to my Richard length times my coefficient times my delta T for copper minus Richard length coefficient times change in temperature for my what you call it, for the steel. All right. And people, here is the formula what I must use. All right, because you can directly see the original length will cancel out. The coefficient I will tell you. The change in temperature you will know. Young's modulus you will know. But what I want is this one and this one. And you know from school days, if you have two unknowns, you need two equations. Now, this is my one equation, but I also know this is equal. That means I can say here that my stress area for steel is equals to my stress area for copper, and then can I say the stress for steel is equals the area copper divide area steel multiply stress copper. Right, and from here I can calculate, here I can say my stress of steel is equals to something stress of copper, and I can sub it in there, and I can start find the two stresses. All right. What I also said to you yesterday, that the stresses here will be, in the problems you will see, talk about tensile and compressed. Now, how do I know which one is tensile and which one is compressed? If you look into your drawing here, can you see my black one is my steel one. From my point here, I put a tensile to that point there. The tensile to that. That means my stress of steel, the answer will be tensile, because I must have a tensile force to bring it here. The one of my copper, I bring it back here. That means the one of my copper, sorry, must be steel. Sorry for that. Must be steel. And the one for my copper is equals to, will be compressed. Right. People do not put a negative there for me and say to me, you have a negative mean compressed. No. You indicate there for me it's tensile or it's compressed. Okay. All right. That is the first part of this. I will continue now to the next part. Is there any questions? Anybody have a question? Anybody have a question? Everyone's happy up to this point? We will do now a real example. Don't worry. We will do a real example. Don't worry. But there's something else what I want to show you. Right. It looks like for me everyone is happy. Okay. There is a hand. Please, people, sometimes I'm not at the point where there is hands and things. You must scream to me, but I see there is a hand now. Bamboo, you can talk? Unmute. Yeah, okay. You can talk. I can't hear you. I cannot hear you. Maybe something is wrong. I think you can in the chat box maybe type in there your problem or send your problem. I understand you have you guys have a group or maybe a WhatsApp group. Send it there, and then one of the other guys can indicate to me what is your question. Okay, all right. Let me continue to the next part. People, the next part is, the next part of this is now, let me first draw it again. And that's my steel one. This one is my copper one. That was my original length. And here now is my line YY. We're standing now at this point here. All right, we are standing now at this point here. Okay. Now I said to you, let me put another load here. Let me say tensile one. I put another tensile force here, another tensile force here. All right. Okay. That means I put it on the steel and on the copper, because this thing is in parallel. Now, what will happen now? What will happen now? With this load here, with this force here, it means, depending on how big the force is, my steel one will going up to there, and my copper will also going up to that point. And who can tell me, this change here, is it a mechanical change or is it a free change? Who can tell me? The mechanical change or free change?
Mechanical.
I can't hear you.
The mechanical change.
Yes, it's a mechanical change because I have a force here. That means that my mechanical change for steel and my mechanical change for copper. That means my mechanical change for steel is equals to my mechanical change for copper. Because inverse, okay, put here, that's the B part. In the inverse here, the question will say, I want the result stress in the steel and in the copper. I want the result stress. That will be my question. I want the result stress here. Right. Now, people, the force here to let verse 2, and that you have already learned with Prof. Desai, the force here to get verse to verse part here, that means verse force is my total force, because there will be a force in the steel and the force in the copper can't be equal. Because if that force is working, the full force is working on the steel and the copper, depend on his size and material, that means the one will go much further like the other one because it's softer. But we want to keep it here. I want the mechanical change to be equal. Right. And then from there you go again. Is my stress area for steel plus stress area for copper, and again I will know what is this. I will know the areas, but the stress I didn't know. But out of this one, I can get my other equation, because we know here stress L over E for steel is equals to stress L over E for copper. We know the original lengths are equal. Then I can say the stress of steel is equals to Young's modulus of steel divided by the Young's modulus of copper, multiply the copper, and then you get something copper, and I can sub it back in here. All right. Then I will done my calculations, and I get the stress for steel, and I get the stress for copper. All right. This load here was tensile. That means this one will be tensile, and this one also will be tensile. Okay. But this is not my result stress. Remember, the result stress is the stress in this whole body. From here to here. In this part, we know the stress was 0. In this part, we have already calculated a stress here. And now we have a stress here. That means my result stress for steel is equals the first part plus the second part. Right, that means first part is this part. Second part is this part. And I will get the answer. The same with a result for the copper is the first part plus the second part. That means the first part is here. The second part is this. And then you get your final answer. All right. Okay. Any questions till this point? Anybody have a question for me up to this point? Right. Looks like people are quiet. The last thing what I can ask you, calculate for me the last thing what I can do is, I can say to you, calculate for me the final length. Okay, the final length is from here up to this point. Right. You can use the steel one or the copper one. It must be equal. It must be the same. Okay. You will see now when we've done an example. It must be the same. Or I can ask you, calculate for me only the change in length. Only the change in length is only then this part. Again, if I do not indicate you which one to use, you can use any one. You can use the steel one over copper one. But if I indicate you which one to use, then you must use that one. All right. That means on the end of the day, this is the change in length, means say the final length, then you must include the original length also. That's the three things what I can ask you. That is the full question. To sum up quickly for you, first I say to you, calculate for me the stresses in the two materials when the temperature change. The B part, if I add another one, so it's tension or compressed, remember that one was compressed, that means this part was moving backwards, then this two was compressed. And then I say, the second part, I want the result stress. When I add one, then I calculate the result stress. And the third question is, calculate for me the final length over the change in length. That is the whole problem of this chapter of temperatures. And that's why you will see when you start doing the problems out of the tutorials, then you will realize that there is a lot of this type of problems, and that I can guarantee you this is the type of thing what you will receive in the test as well as in the exam. Right. Okay. Any questions up to this point? We're going back and see if there's any hands. Anybody have a question for me? Anybody? Right, it's quiet.
Sir,
Yes.
can you please go back? By the time when you say, when we calculate the result, the rest,
Yes.
you say we add
Yeah.
the stress 1 and stress 2 for the
Yes.
steel and also for the core.
Yes.
So the stress 1, is it when we bend the materials?
The stress one is the one. Stress one is the one when you have a temperature.
Okay.
You have a temperature. Okay. And the second part is when I add another load. You will see now with the example when I add another load, extra load. Can you see? This is this one's here. Then you add the one by the other one.
Okay.
Okay, understand?
Yes.
All right. Okay, people. Here's the question. Sorry. The example, what we will do. Right? You say to you, you have a brass rod, 25 millimeters in diameter, is enclosed in a 10 millimeter. Yes.
I don't see the screen.
Maybe I freeze. Let me quickly check. Okay. Sometimes the screen freeze because I wave my hands under it. Yeah. Okay. Let me see if you can see it now. Can you see it now?
Yes.
Right, good. Can everyone see it? I hope so. Right, again, we say to you, you have a brass rod and inside the steel tube is 100 meters long. Calculate stresses in the two materials when the temperature is raised by 100. Okay, that's the A part. The B part is saying, if there's now an extra actual tension load of 50 kilonewtons, find the result stress. Okay? And then the C part is find the final length of a composite rod. And he indicate you what is Young's modulus, and he also indicate to you what is the coefficient. Now, people, if you are a guy and you do not know which one of the two materials is the softer material. That's what I say to you. If you look into the coefficients here, you will see the steel is 12 and the brass in this case is 19. That means the one with a higher coefficient value is the one what is the softer material. Okay. Right, come. Let me start with this one and see how far can we get till the class is finished. Right. What I first want of you, start draw it for me. Make for yourself a nice drawing with all the values. Some people do not waiting for me. I was jumping in now with you guys. Right, let me start. Say to you, you have a steel tube. And a brass rod. Say to you for the diameter for brass is 25 millimeters. The tube, the outside diameter for the steel is 50 millimeters, and you have a thickness of 10 millimeters. Who can tell me what is the inside diameter for the steel tube? What's the inside diameter? Can tell me inside diameter? Anybody? You can tell me what's the inside diameter?
D squared.
No, well, what is the inside diameter? Tell me. What's the value? The outside diameter is 50 millimeters. What is the inside one? Because we have a thickness of 10 millimeters. What is the inside one? Some people tell me, well, what's the inside diameter? What's the inside diameter?
It might be 30, sir.
30. Thank you. 30 millimeters. And they also indicate to you that you have a change in temperature equals to 100. And when you tell you what Young's modulus is, I'm a poison actor. Okay, the first thing is what we know, heat change. That we say is my 3 chains of steel, and then you have your copper. From here to here is my 3 chains of copper, and then we have your line Y, Y, okay, and then we say, okay, to get it back to my line Y, Y, first thing what we know the force in the steel must be equal to the force in the copper to bring it, okay, what is at Y, Y, at line Y, Y, okay, the stress area of steel is equal to, what is brass, sorry, copper, brass. Is the stress area brass. Stress of steel is equals to the area of brass is pi over 4 0.025 square divide pi over 4. For steel one, it is 0.05 square minus 0.03 square by brass. Okay, steel is equals to, can anybody calculate for me and say what is the steel? The steel is equals to the brass. What is the value? Ratio between the two. Anybody have an answer? Anybody have maybe an answer for me?
I got 0.391.
Yeah, the same with me.
Right, good. There's number one. Please, people, do not sit there and only copy. I want you to be part of the group. Please, do not be only a visitor, please. Right, now we know. Then the next part was that your mechanical one for steel plus mechanical one for the brass will be equals to the free change of brass minus the free change of the steel one. You can remember that one. Okay. Stress area, stress L, sorry, over E for steel plus stress L over E for brass is equals to L times coefficient times delta T for brass plus L times gamma times delta T for the steel part. All right, that is my formula here. Okay. Now, in the place of my steel, can I say 0.39 the brass one? Because I know that my original length will cancel out because it's equal. That will cancel out. Okay, divide by Young's modulus for steel is 200 times 10 to the power 9 plus the steel of brass over 100 times 10 to the power 9 is equals to 100 for the change in temperature minus 19 times 10 to the power minus 6. Sorry, that one must be minus also. Minus 12 times 10 to the power minus 6. Right. From there, you can calculate for me what is the stress of brass. And after that, you can tell me what is the stress of steel. That means now that we continue there. I want that to tell me what's the stress of brass. And then the stress of a steel part is equals to 0.39 when you have answers. All right. Then for that calculation, then you can indicate to me what is the answer for the brass one. What's the answer for the brass? If you have an answer, you can inform me what is your answer for brass.
For brass, I got 58.58 megapixel.
58.58
Yes.
megapascals, right? Multiply 58.58 and then multiply with 0.39 when you will get
22.85 megapixel.
85 megapascals. Right, people, now in the case, who can tell me the brass and the steel, which one is tensile and which one is compressed, or is both tensile or is both compressed? The brass one, is it tensile or compressed?
The brass look like compressed.
Why you say look like compressed?
It's being forced back.
Yes. The reason for that compressed here is because, remember, I compressed it back here with my force in brass. Right. The one why I say it's tensile here is because I move it till that point. That's why it is tensile. I pull it. Right. That's the first question. Any questions? Any questions? Everyone happy? Because now we put in real values, and you can see how it is going. Right. See, there's no hands. Right, people, now let me move to the second part. The second part of a problem, say, you put now extra load of 50, find the result stresses. Right. That means, again, you have your material. We have this point now here. Yeah, at y now here. Okay, this one is my steel, and this one is still my brass one there. Okay, now I put that extra load. You say it's a tensile one. It means it's a tensile one of 50 kilonewtons. Right. Now what we know it is everything moved to a certain part. And out of this, can I say my mechanical change for steel is equal to my mechanical change for the brass one. Okay, and in this case, we know SL over E is steel is equals to stress L over E, and that is for the brass part. This cancels out again. Stress of steel is then equals to 200 by 100 stress of brass. I mean, I can say if my calculations is correct, I can say my ratio between the steel and the brass for this part is the one is 2 times the other one. All right. Then we also know now that the total force, that force of 50, is equal to the force in the steel plus the force in the brass. And that is stress area for steel plus stress area for brass. 50 times 10 to the power 3 is equals to. In the place of my stress for steel, I put there in 2 times stress for brass. Right, multiply when the area for my steel one, it's pi over 4, 0.05 square minus 0.03 square. Right, that is for that one. Okay. Plus stress for brass, multiply, that one is 25 pi over 4, 0.025 square. And that is for this one. Right. Then you can calculate for me brass is equals to what? Brass part is equals to what? And then my steel is equals to 2 times. Okay. Let me first calculate first for me what is the brass. If there's anybody have an answer for me, please indicate to me what is your answer for brass.
We got 16.64 megapixel.
16.64 megapascals. Okay, 16.64. And then for your steel, multiply that by 2 will be what? 33.28
28.
megapascals. Right, people. This steel and brass, is it tensile or is it compressed? Which one is tensile, which
Tensile.
one is compressed? Okay, the brass one, is it tensile or compressed?
Yes.
Yes.
Even the steel.
Okay, both is tensile because that load, this load is a tensile load. Right. Now we're going, you want the result stress. The result stress for steel is equals to, now when I'm going back to my previous part, I know for steel it was 22.85 tensile. It is 22.85 plus, because that was also tensile, 33.28. And you have your answer. The result one for brass, the result one, in the previous one, when I check, it was 58.58 compressed. 58.58 compressed, it means I must put a negative in front, plus 16.64. And then you get your answers. All right. Anybody have an answer for me for the steel one?
First one is 56.13.
It's what? How much is it? The steel one is 56.13
13. Yes.
megapascals. And you'll see my answer is positive. It means that one is tensile. Okay. For my brass,
75.22.
can't be 75. Remember, you
It's
have a
minus
minus
58.5.
58.5
I
like that.
didn't see minus. I didn't.
Come again?
Minus 41.94.
41.94 megapascals. It is minus. It means it is compressed. Okay. That is my second part of my question. Anybody have a question for me on this part?
Yes, sir.
Right, it looks like everyone is happy up to this point. Now let me coming to the last part of the question. The last part of the question say, calculate the final length of a composite rod. Right. Now you can indicate to me, do you want me to working with a brass one or with the steel one? Which one you want me to work with? Right, it's quiet. So then I must make the decision. Let you working with a brass one. The C part, we're working with a brass. Okay, now people, if you're going back to my drawing here, you say you want the final length. Right, you want the final length. Okay, that means it's my original length, plus the part here. That means it's my pre-change for brass minus my mechanical change for the brass part. Right? That is one up to this point is my free change minus my mechanical change. Right? For this part here. Plus, we're going to this part plus my mechanical change here for the 51. The mechanical change for the brass when it was the load of 50. Right. You have indicate to me, right, let me put over its length plus your length multiply coefficient multiply free change minus stress L over E plus stress L over E, and this one is for the 50 load. Okay. Now I say the length you have indicate to me, the length is 1 meter plus 1 multiply, what is the coefficient was 19. 19 times 10 to the power minus 6 multiply 100 minus the part there. What was it there? It was 58.58. 58.58 times 10 to the power 6 multiply 1 over 100 times 10 to the power 9. Okay, that was that one. Plus, for the next one, for brass, it was 16.64 times 10 to the power 6 multiply 1 divide by 100 times 10 to the power 9. Right, and then you can calculate for me what is the final length. It's supposed to be 1 comma something. So that one is a meter. Anybody have an answer for me? Anybody have an answer for me?
I got 1.710.
1 point?
711, yeah.
It can't be. When I calculate it. Anybody else have an answer for me?
Sir, I got 1,0014.
148 meters.
Yes, sir.
That's my answer, what I get. Yeah, okay, that's the right answer. Right, people, can you see? This is everything what I can ask you in the exam or in the test. The thing is I hope you can see what is the difference what we have done yesterday and today. Well, you can see when in this case we have two materials and yesterday it was one material. This is on the end of the day to go back to the previous one. This is the formula when it is in series. One is inside the other one. The other part, what you will pick up when you're done with problems, is when we say we have materials in series. Say that's one steel one, and this one we say is a aluminium one, for example. When it's in series, everything is the same, people. Nothing changed. Only what changed if you've done this whole proof again. What I done here, you will realize that when you came into this one, you will say your mechanical one for steel plus mechanical one, in this case for aluminium, is equals to the free change for aluminium plus the free change for the steel. That is what? The other thing is the forces of the steel is still equals to the forces of the aluminium. Everything of that is still the same. Only what will change here is from this formula to this one. That one is a negative, this one becoming a positive. That's the only thing what will change. And you can go and test it to go through this whole process again. I do not want to do that everything again, but this is the proof of the formula if a guy asks you to prove the formula. Right, that is the way you prove a formula. And that is the only thing. That means you have now 3 formulas. The one formula, the first formula, is what we have done yesterday. If you can remember, yesterday we have, what I show you earlier this day, it means you have, let me write it on a piece of paper for you, and you will see. Your one, what you have is your stress is equals to your gamma times delta T times Young's modulus. That's your one formula. That is the formula if you have one material. This is for one material. Okay. Then you have your next one. What we done, what we say, stress mechanical for steel plus mechanical, say for the softer one, copper, is equals to my free change for copper minus my free change for the steel one. Right, that one was when you have 2 materials. That one is steel, for example, and this one is copper. That means it is in parallel. Okay. Then your last one, what I said now to you, is if you say you take a steel again, plus softer material is equals to a free change for copper plus free change for steel. This is it when it is in series. That's my steel one, and that is my copper one when it is in series. Right, that is your 3 formulas on the end of the day, what you will use here. And also what you will use by verse 2 is that you know your forces in your steel is equals to your forces in your softer material is equal for that part at y that you have there. Right. And also here for this one, if you have can I say extra load, you have a total load, then from there you know that is equals to your force of your steel plus your force of your copper, that part there, and your mechanical one for your steel is equals to your mechanical one for your copper. That's also important. That is all the things what you need here to complete this problem. And the last part, what I said to you, he can ask you to calculate the final length or the change in length of any one of the materials. All right. That is the whole chapter. That's everything about the chapter. You will, what I said earlier to you, you will see that, for example, especially in your textbook, also what you use now, I already checked there. If this people say when you come to the, say, steel plus copper is equals to a free change, copper minus free change of steel. In the case here, I use the whole time stress. That guys use FL over AE. For steel plus FL over AE for your copper is equals to your well, delta T for copper minus for the steel one. And then from here, the guys will calculate what is the force for steel. Right, you will get the answer. Because you know the force for steel and for copper is equal, you will get the answer there. And from there, in the textbook, when you will say the stress of steel is equals to the force over area. That is the other way what the guys are doing it. In the case, but then you must know that your forces are equal here when you're going this side. In my way, the way I have done it for you now, because I ask you what is the stress. If I have asked you what is the force, yeah, then it's much easier to do it this way. But I directly ask you what is the stress, and then I put stresses here, stress L over E, and I get the ratio between the two because I know these are equal. Right, but if there's more than one way, and I said again, you can go and you can decide for yourself which one is the best method for you, the way you want to do it. If your mathematics is 100% correct and you have the same answer what I have, I will definitely not mark it wrong. I will mark it 100% correct. All right. Any questions from anyone before I say goodbye for you to enjoy your long weekend? Right, there's one, Mr. Foster.
So just a quick question. Is it possible for you to just upload the PDF? So yesterday you printed out papers with questions on them. Is it possible for us to have access to those questions and the way you did them?
Which one you're talking about now?
Sorry, it was in yesterday's class. The questions we handled in yesterday's class.
Yeah, but that questions is on that slides.
Oh, okay, perfect. Oh, thank you.
It's on the slides. It's on the slides. Check the slides. It will be there.
Okay, thank you, sir.
Okay, all right, good. All right, people. Now it's in your hands now. To start, I said to you, there is a tutorial like this in your D2L. I put the tutorials for you, and then there is in each chapter there is for you 10 problems. And if you can do all those 10 problems, I'm 100% sure you will get nearly or full. You're supposed then to get full marks for these chapters in the exam and in the test. That's why, please, what we have done this morning is more or less what I can ask you. I have other 2 problems, but I also, and I think it's a 1 hour problem. But I want you, what we will work through next week, say this time again. It is something what I am more a real mechanical one of when the guys tighten nut and things. I do not think that one is in your tutorials, but I will look for that one, and I want us also to going through that one as well, because that's also a good example. But now next week, Wednesday, 1 o'clock, it's up to you. You must ask me, indicate to me which one you struggle with, and then we can work through it. I will do not, be honest with you, I will not sit here and do all 10 problems for you. No, that's not the way I'm working. Have a lecture on maybe doing that? I'm not. I said again, if you try a problem and you have a question, you didn't get the answer, you're welcome to email it to me, or you're welcome to set up a MST link that we can talk, or you are welcome to come to my office. Make an appointment with me. You came here and I will help you. I'm here to help you, but I'm not here that you sit here and copy everything. I want you first to work and check, can I do the problems where I make the mistakes, because I want to see where is your mistakes. For me to sit here and done everything for you and you copy it, when you come in the exam, you can still not do it. Right. That's why, please, people, I know it's long weekend. Some of your guys is maybe going away and do not want to do any university work. But remember, when you have a day off, that is the time where you can sit and study. You have a whole holiday later on this year, and you have a holiday at the end of the year in December. That's why use the time and make sure that you understand the things and you're up to date when you are coming back next week, Tuesday, to continue with your studies. Right. Enjoy your weekend and be safe. And we will talk again next week, Wednesday. See you. Bye-bye.